Hi students, welcome to another video on OPamp circuits. So in this video, we actually do simulation using LT-Spice and try to verify what is the gain, what is the bandwidth for both inverting and non-inverting amplifier. So let us proceed with, in the previous video, we have already seen for a gain of -10, we know that this is the inverting amplifier. So let me just do the frequency response of this. So let me just note the values what I have. So R1 is 1 kilo ohm and RF is 10 kilo ohm. So let me get to find out the gain and bandwidth. Let me double click on this V out. You have two cursors. Place one of the cursor at lower frequencies. Place the other cursor so that this magnitude difference is -3 dB. So that corresponds to half power point. So let me just move it so that it is -3 dB. I'm there. So let me now the gain in dB is 19.99 and that is 19.99 dBs. Let me find out what is AV in volt per volt. So that I will do it as AV in volt per volt is nothing but 10 to the power of, let me show you that. So this is AV in volt per volt is 10 to the power of AV in dBs divided by 20. So this is the expression. Let me know what is the bandwidth. So bandwidth is actually this, which is 80.3 kilohertz. Let me make it as 80 kilohertz. So this is, let me write it as kilohertz. This is ohms. This is ohms. So let me write this because it's already in dBs. So let me find what is this 10 to the power of 10 to the power of 10 to the power of 19.99 divided by 20, which is close to 9.98 into 80 happens to be 799 kilohertz. 799 kilohertz is the gain bandwidth product. These are the values that I have for this is the frequency response of an inverting amplifier. You can also see there is a phase. If I write the phase of it, let me write the phase over here. You can see because we know that in case of inverting amplifier it is out of phase. To find out that, you can see this dotted line is phase, this solid line is the magnitude, because this is the Bode plot of Bode plot matlab it's a frequency response which is having both magnitude as well as phase. You can see here there is a magnitude and a phase. So phase is 179.98, which is almost close to 180 degree. So 180 degree corresponds to 180 degree corresponds to a out of phase property. Okay, this is what for a gain of 10. Let me just do it as 1k and 50k. Let me change this to 50k, 50k, and then do the simulation. I've done the simulation. Okay, this is my DC gain. DC gain matlab at low frequencies. Let me keep this so that it is 3 dB down. Just sorry. Okay, I'm almost close to -3 dB. Okay, you can see this is what is -3 dB you have. So now for gain in dB happens to be 33.9 dBs and bandwidth is 16.75 kilohertz. So what is 10 to the power of 33.97 divided by 20 is 49.9 is the gain. We expected -50, of course. I'm just writing the magnitude here, and it is now 49.9 multiplied by 16.75. Now it is 836. So this is the reading what I'm having now. This is the reading what I'm having. So you can also find the phase of it. Phase is, you can see it's almost same, 179 degrees or 179.9 degrees, which is equal to 180 degrees. Let me change this to, okay, let me give it as 10K and 1K. Now I'll make this 1K and make this as 10K. So I should get a gain of 0.1, which is minus 20 dB. Let me run now. See, now you have a gain of minus 20 dB. Of course, you can see this is going up, which is not intended. Okay, let us, of course, you can certainly verify the gain, which is minus 20 dB. The phase, sorry, the bandwidth is not a relevant parameter since the gain is less than 1. So usually when the gain is less than 1, we will not actually find the bandwidth. So let me make this is minus 20 dB. So minus 20 dB is actually 0.1, and this bandwidth and gain bandwidth product is not relevant. See here, 10K 1K for this, as per this ratio, this should be minus 0.1. So of course 0.1 is nothing but minus 20 dB. Again, this is minus 20 dB corresponds to 0.1 as the gain. So this is dB is negative. So when dB is negative, it is a gain less than 1. Gain less than 1. So this bandwidth and GBW is not relevant since you are doing it for gain less than 1. So now let us do this non-inverting amplifier. Of course, you can see here the phase will be still 180 degree. You can have a look at it. See here, this is still 180 degree. This is 179.99. So it is 179.99 degree. It is out of phase. Now let me do this for a non-inverting amplifier. What I'll do is I will move this from here to here, and I will use wire to make the connection. So this is as simple as that. So this is my non-inverting amplifier. Now the gain, let me make a gain of 2. So for a gain of 2, both should be 1K 1K. So as per this, so let me make, because it is 1 plus RF by R1, if I make both the resistance same, then the gain is 2. So what I'm having now, this is non-inverting amplifier, which is 1K. You are expecting a gain of 2. That is, what is 20 log of 2? 20 log of 2 happens to be 6 dBs. So let me see what is the magnet you are getting. Let me run now. You can see now you are getting 6 dB. See? Okay, let me double click on this. Sorry. So now see here, this is 6.02 dB. You can see the phase is almost 0 degree. This is minus 2 milli-degrees. Milli-degree is almost like 0 degree. So let me keep this at 3 dB down so that I can find what is the bandwidth. Okay, I'm there. For 1K non-inverting amplifier, the gain is 6.02. The corresponding volt per volt gain is 2. The bandwidth is 392 kilohertz. So it is 392 into 2 is 784 kilohertz. 784 kilohertz is my bandwidth. Sorry, gain bandwidth product. So I'm just showing you this. So this is for non-inverting amplifier. So and so. Let me do it for 1K and 22K. RF, let me make it 22K. You can just repeat this for different values. So let me make this 22K. So for 22K, I'm going to get a gain of 23. What is 20 log of 23? You should get 27.32 dBs as my DC gain. Okay, this is, when I say DC gain, it's at low frequencies. So at very low frequencies, what is gain? We call it as DC gain. Because DC has got 0 as the frequency. So when you're operating at, when you're measuring at low frequency, we call it as DC gain. That is very low frequency, which is 10 Hertz is very, very low. You can see it is now 27.23, which corresponds to a gain of 23. Of course, you can do 10 to the power of 27 base also. So let me adjust this to minus 3 dB, which is not there now. Let me make it at minus 3 dB. I am there. Okay. So this is now the frequency, the bandwidth is 37.7 kilohertz. Now what is the gain bandwidth product? 23 multiplied by 37.7. You can see it is 861. So 867. So I have, you can see gain bandwidth product is almost not too much of a variation. Okay, let us do for one more. Now let me do, okay, I can make this this you can make it as around, okay, 120k or 150k. 150k will going to end up with a gain of 151. So what is 20 log of 151? 20 log of 151 is 43 dBs. Okay, how much is the gain? You're getting almost 43.57, which is the expected one. See the bandwidth. Bandwidth is now minus 3 dB. Okay, I'm there. Okay, this is, so this is sorry, 1k, and 150 kilo ohm is your RF. So it is 43.57 dBs, which corresponds to a gain of 151, and the bandwidth is 5.66 kilohertz to 5.66. You can see it is 246. Okay, gain bandwidth product has reduced a lot, so it's not remaining constant because we are operating with, okay, this is a concern now. Gain bandwidth product has reduced. Okay, this is how you can able to, of course, more interestingly, just see the phase of this. So in the previous cases also we didn't measure the phase. You can see here, this, the phase is almost 0 degree, minus 326 milli degrees. Don't simply go by that minus 326. It's actually milli. Milli means 0 degree, 0 degree, 0 degree, meaning there is no phase shift. So input and output will be in phase with each other. When I say in phase, if this is your input waveform, the output waveform may be amplified one, but it will be in phase. So, and this increases, this also increases. When this reduces, this also reduces. So likewise, you can just, okay, very different values of RF and RL. Let us move on to another circuit where you have inverting Schmitt trigger. So let me just rig up this circuit over here. So what I want to have is, let me flip this. If I flip, that will become a Schmitt trigger. So how do I flip it? You can select that. You can select it. So let me select this. Okay, once I select, do Control E and Control rotate twice. So now this is my, here this should be minus, this should be minus, it is minus VCC, this should be plus VCC, this should be plus VCC. Is this not the Schmitt trigger? See here, this is plus minus, which is exactly this circuit. See here, it's exactly the circuit. So here it is, we can just have a look at it. We're just having a similar circuit here. Okay, let me do this. Let me take out this for the time being. Let me see now. This is minus, which is minus going to this. Okay, let me have an AC, not an AC signal. Let me have a sine wave. Sine wave of 0 offset. Let me give an amplitude of 5 volts, and let me give a frequency of 100 hertz. That's it. Okay, this AC amplitude we can take out. This is done. And let me have a reference voltage. I'm putting a reference here. Let me have its reference. So how do I have reference now? Okay, control C is for copying. I'll copy this and then paste it. Let me make this as the reference. So this is a none. Make this as initially 0 volt. So this is a reference voltage and this is the sine wave. So let me just put it aside. So what I'll do is I'll take this and move it a bit. Okay, this is my sine wave. Okay, let me do the transient now because AC sweep is not recommended now. So I had to do the transient which is there here. 50 millisecond is enough because I'll see 5 cycles. So now output will go to plus Vsat minus Vsat, which is plus 10 minus 10. Of course, let me make this okay, maybe 120k. So you can, or maybe you can just take it as 1k or 10k 10k for simplicity. Let me make it this also as 10k. This also has 10k. Now let me run this. So when I run, okay, let me just run it again. So let me measure this input over here and the output. Let me take out this N001. So what is N001? How do I take out? Press delete. This will go off. Now, okay, I'll just put this also together with that so that it will be easy for analysis. So let me just change this scale to some larger larger. Okay, let me delete this also. How do I delete? Let me delete this pane. Okay, let me change this access setting to a different voltage. Let me make it as okay, maybe 12 volt to minus 12 volt so that you can see that see now this is more relevant than the previous one. Now let us try to understand what's happening here. So now when the input voltage is increasing, what is as per our circuit, what is the expected VTH VTL? So we know the expression for VTH VTL, which is this. So since I'm measuring it as 10k 10k, the VTH VTL happens to be exactly 5 volts, correct? It's exactly 5 volt. So that's why when the input voltage is reaching plus 5, it is making a transition. Let me make it up to maybe let me make it up to 10 volts here, or maybe 8 volts. Now if I run it again, now it is, oh sorry, it has become 80 88. Let me make it 8 volts. So what to observe here is, again let me change that scale, that is skip. If I run it, it will become by default. Okay, see now when the input crosses, of course that's how your Schmitt trigger operate. So when the input voltage crosses VTH, so let me just zoom this out. Let me just zoom this out. This is my input. Let me just move the cursor on this. When the input voltage is, just have a look at that input. So when the input is exactly 5 volts, let me further zoom this. So now it has already, see here, it's almost 5, or that is not 5. Let me just go to 5 and try to see what is the condition of here. This is 5. We can just zoom it out. See here, at that 5 volt output is making a transition from here, because this is the transition has started. You can see the voltage is 5.05 volt. The transition has started. So this is your VTH. So when the input voltage is 5 volt, output has started the transition. So this is VTH. How do you find VTL? Again, just zoom it out. This is the transition point. See here. So now let me move this. Now whenever the input is minus 5, so here can you see this is almost minus 5. This I'm moving on a green one, which is, sorry, the red one, which is input. When the input is trying to go below minus 5, you have a transition from minus VC to plus VCs. So this is the Schmitt trigger. This is a Schmitt trigger. If you want to see that hysteresis, so if you want to see the hysteresis, it is possible to do that. You can change this from time to V. Suppose if your x-axis is input, then this will become a transfer characteristics. So what should be your x-axis? Here you can see this is your input. So if I change from time to V of n003, V of n003, you can see this is your transfer characteristics. Let me just change this to, okay, sorry, let me change the scale to okay, 12 and minus 12, minus 12, minus 12. See now, see. Okay, let me take out this. This is your input. Let me take out that input. How do I take out the input? Okay, delete, and this. This again change to the earlier scale. Now whenever you do some operation, it will go back to that. This is now, this is 12, and you can change this to minus 12. This is minus 12. See now, this is VTH. So at this point it is plus 5 volt. Output is going from plus VSAT to minus VSAT. It's going back here. The output will go from minus to plus when the input is minus 5 volt. When the input tries to go below minus 5. Suppose if I change R1, R2s, then this will shrink. So this will shrink. So what I'll do is I will change the value of if I reduce the value of the bottom resistor that is there towards the, okay, let me show you that. If I reduce this resistance, then your hysteresis will reduce. Let me make it 5K. If I make it 5K, what will be your what will be the VTH VTL? Sorry, it is become 5K. So it will be 5K means it is 10 into 5 divided by 15. So it is 3.33. So now this is happening at plus 3 and minus 3, sorry, plus 5 and minus 5. That will become 3.33 and minus 3.33. The moment I run it, you can see it shrinks. You can see now this is becoming, this is actually 3.33, this is minus 3.33. And of course this is due to that the initial waveform that what you're getting. So this is not valid one. Suppose if I make it still 1K, if I make it 1K now, it will further shrink. So if it is 1K, it will be 10 by 11. 10 by 11 is almost 0.9 volts. So this will make a transition from plus to minus, plus VSAT to minus VSAT at 0.9 and minus 0.9. See now, this is happening at 0.9 volts. So this is happening at 0.9 volts, and this is again happening at minus 0.9. So this is hysteresis depends on R1, R2. Suppose if I have some positive voltage, you can see this will entirely shift. So I just want to show you here. So what I want to show here is okay, let me just do this. Suppose if I make this hysteresis, sorry, V reference voltage more and more, the VTH VTL which was there happening at equidistance from the y-axis, it will now either, now you can see it is moving closer to the positive side. So it can be here also. The entire both positive negative can be, sorry, VTH and VTL both can be positive, or it is also possible to have VTH VTL both negative. So this shifting of your hysteresis depends on the V reference, and the width of this depends on R1. The width of that depends on R1. So what I'll do now is I will make this equal to maybe 3 volts. You can see where it goes. Can you see it has moved here? So it is now both are positive. So you can see both are positive. Suppose if I make it 1 volt, if I make it 1 volt, you can see one is slightly negative and the one is positive. If I make it maybe minus 2 volts, let us see what happens. It both are becoming non-negative. Both are becoming negative. So what is VTH? VTH is this, the input voltage at which that transition happens is VTH. So maybe let me just measure here. We can measure VTH here also. How do I measure VTH is? Okay. How do I measure VTH? Okay, now it's keep moving along that. So another way of this, of course, the transition has started here itself. It's around 900 millivolt. Of course, you can make the measurement here, or if you want to see the waveform and do it, you can certainly do that. How do you do that? Is go here, make this axis setting as time. The moment I make this as time, you can see you have the waveform. Okay, what I'll do now is I will take that what is that? Okay, input also. How do I take the input? Either you can go to add traces and look for VN001, which is my, oh, N001 is not the input. So when you have difficulty, what you can do is you can just label that, let me label this as VIN. So what I'll do, I will use a net and name it as input. So when you name it as input, so this node will be treated as input. If I run it now, if I want to see the input, go to add traces. Can you see there is something like V input? This is your input. So you can now, you have a precise name for that input, so that you will not be having any confusion. So what I'll do here is I will remove this. How do I remove? Delete and then take out this. Now if you want to measure VTH, VTL now, just zoom this portion, move your cursor on. Okay, you can just further zoom it. Move the cursor on your see, this is where the transition is happening. See here, this is a transition happening from minus to plus. What is the corresponding input voltage? The corresponding input voltage is minus 2.8. Minus 2.8 for a reference of minus 2 and for R1 R2 of this. So this is VTL. So this is going from minus V side to plus V side. What is VTH? VTH is here. VTH is, just see where this transition starts. So now I am just moving this so that the transition is starting now. What is the, maybe you can just further zoom it. See now. So maybe this point. Okay, the corresponding input, maybe you can slightly go back. Okay, here. So what is, this is cursor 2. Cursor 2 is over here. It is 8 minus 809 millivolt. So because this is 0, this is 0, this is around 0.8 volt. 0.8, of course, minus 0.8 volt. Minus 0.8 volt. This is VTH, because output is making transition from plus V side to minus V side. So likewise, so maybe we'll just note one such values so that you can do it for that. So how much is okay, let me name it as R1 R2 in our usual pattern. So this is R1 as per our circuit. This is actually R2 as per our circuit. And then let me name this as V reference only so that you don't have any confusions. So this is V reference. Let me start with 0 for one such reading. Let me run now. So for a value of R1 R2 as 1k 10k. How much is R1 is 10k. What is okay? R1 is 10k, R2 is 1k, V reference is 0. What is VTH? VTH is actually here. Okay, somewhere here approximately. It's 850 millivolt. 850 millivolt, and this is okay. Let me. This current also came. Okay, let me delete this. Okay, and let me just move on to find what is VTL. VTL is the point where it is making a transition from minus to plus. Somewhere here. Okay, which is now minus 1 volt. Minus 1 volt. So now these are okay. You can find what is plus Vsat minus Vsat also. So this is plus Vsat minus Vsat. Let me measure that value. So for 10k 1k and V reference of 0, this is VTH is 850 millivolt. This is almost minus 1 volt. Of course, there'll be slight error in measurement exactly where it has started the transition. So you may have slight different values here. You may end up with 870 or 950, or this can be minus 950 millivolts also. So that's okay, fine. So let me also measure what is VTH VTL. Plus Vsat minus Vsat. So this is plus Vsat is 9.99 and the other one is minus 9.93. See, this is plus Vsat minus Vsat values, which is here. So it is plus Vsat is 9.95, minus Vsat is minus 9.96. It's almost 10 volts, plus or minus 10 volts. So you can just play with this, make this equal to 3 volts. Then your VTH, VTL will change, and measure again the input voltage at which output makes a transition from plus to minus and minus to plus. This is, sorry, let me just do this. So zoom a area where you can see both transitions. So move this on. Okay, I need to move it on the input. Okay, let me move this. Come on. Let me zoom only portion. This corresponds to transition from minus to plus. This second one corresponds to transition from plus to minus. So second one is VTH. VTH is now in this case which is second. This is cursor 2. It is 3.79. 3.79 is VTH. VTL is that is first cursor. First cursor is 1.64. It is 1.64. So it is for a value of 1k. R1 is 1k. Sorry, R1 is 10k. R2 is 1k, and you have a V reference of 3 volt. Can you see both have become positive? VTH, VTL both have become positive. So this is V reference 3. This is 10k, 1k. This is 3 point. This is 3.79. This is 1.64. So both are positive. Both are positive. Suppose if I make this minus 2 volts, to make it minus 2 volts, and if I run again, the transitions will happen. Maybe you can just reduce it to hardly not this. The time response, instead of zooming, what you can do is you can see only one cycle. How do I see only one cycle? Is make this time period hardly maybe 20 milliseconds. You'll see only 2 cycles. See now you move along. I'm having 2 cursors, so let me put one cursor for minus to plus transition, Okay, cursor 1 is from minus VSAT to plus VSAT, and let me put cursor 2 for plus VSAT to minus VSAT cursor. Okay, the cursor 1 is VTL. Cursor 1 is VTL is minus 2.35. VTH is cursor 2. This is cursor 2. This is cursor 2. Cursor 2 is VTH, which is minus 1.31. This is again for 10K, 1K, and minus 2 volt. So these are the values that I have for 10K, 1K, minus 2 volts. You can see VTH, VTL both are negative, and again in all the cases VTH is always more than VTL. So this way we can able to conduct experiment comfortably using LT spice. Hope this will help you in solidifying the concept that you already know about this. Of course, there is another way of doing this hysteresis. In that case, we are actually sweeping the voltage. So what I'll do here is, I will not use either tran or dot. Okay, dot AC. Of course, dot AC is not used at all for this. So instead of this, what I'll do is I will do dot. This I'll do DC sweep. The sweep that I'm doing is for the input, which is V3. This is V3 source. The sweep is linear. Okay, let me sweep it from, okay, what I'll do is let me sweep it from minus 2 to, or minus 10 to plus 10 with an increment of 0.01 volt. If you run it, you can see this. See here, transition. Okay, this transition has happened. So this actually corresponds to what? This corresponds to VTH. This corresponds to VTH, which is actually, what is x-axis, around minus 888 millivolt. That's what we got it. Let me just zoom it here. So here, wait. This is the transition. Okay, here this is around how much? 927 millivolt, minus 927 millivolts, which we wrote it as, okay, minus 1 point something volt. So this is VTH. So how do you know VTL? So to know VTL, you may have to sweep it from minus 2. So what do I do for sweeping? What I'll do is, let me go here and then change this sweep from, let me make it, sorry, this is DC sweep. Let me make it from 10 to minus 10. This is 10 to minus 10 with an increment of that. You can see you have this. Can you see now? This is actually VTL. VTL is coming out to be minus 2.6. So that's what we had. So this is more negative than more lesser than VTH. So this is corresponding to, because this is that value, minus 2 point something, minus 2.6. So that's what we had here. We actually got minus 2.35 using, of course there it was slight approximation. So using DC sweep also I can measure what is VTL, VTH. We are getting this so and so. Or if you are doing time response, so what I'll do is I will simply change the exactly remains the same. Instead of having this, I will go for dot tran 20 millisecond. If I run, I'll get it. So if you add sine wave also, what I'll do, I will add traces, which is input, sorry, two outputs came. Let me add one more trace which corresponds to input. You have this. Now if you want to see the transfer characteristics, easy way is replace this from v of input, because you want to have the x-axis to be as input. See now? Okay, now you can take out this. Can you see this is your hysteresis? So you can, how do I take out the trace? Delete trace is there, or you can just use this delete symbol and then delete this. You can see, because actually there are two outputs are there. Okay, this corresponds to VTH, this corresponds to VTL. So this is how you can comfortably do time response as well as the hysteresis. To see hysteresis, the axis should be changed to time, the input. In order to see the waveforms, you have to change the axis to time. If you want to clearly see this, change the scale to, okay, maybe you can make it 15 and -15. It will be very clear. This is how you write in your notebook. Of course, you'll have a reference line of 0 and then 0 there for the input output, so that will make it perfectly fine. Thank you.